Good afternoon, dear students. So far we have discussed in thermodynamics, zeroth law of thermodynamics. Today, now we are going to discuss about the first law of thermodynamics and enthalpy and heat of formation, standard heat of formation. These are the three topics which we are going to see today. First of all, first law of thermodynamics. First law of thermodynamics. Or law of conservation of energy. So we can say first law of thermodynamics or law of conservation of energy. So what is the first law of thermodynamics or a law of conservation of energy? There is no change in energy in isolated system. Though it may changes from one form to another. This is a first law of thermodynamics. What is it? There is no change in energy in an isolated system, though it may changes from one form to another. So simply we can say energy remains constant. That is a first law of thermodynamics. So internal energy from the system U. Internal energy can be given by U. For the state from 1 to 2, it is internal energy of state 1, that is initial state. U2 is the internal energy of the state 2. Then totally U2 minus U1, that is equal to del U. That is a change in internal energy. How the change in internal energy may be observed? We can gain the change in internal energy from the heat absorbed and work done. So the mathematical representation of the first law is del U equal to Q plus W. This is a mathematical representation of the first law of thermodynamics. Del U equal to Q plus W. There is a quantity of heat absorbed or released, that is work done by the system or on the system. Okay. Del U, internal energy change. Internal energy change can be given by Q plus W. This is a mathematical representation of the first law of thermodynamics. So what are the various forms to express the first law of thermodynamics? This is one thing we say that there is no change in energy in an isolated system, though it may changes from one form to another. Okay, this is one. The same theoretical explanation can be given various ways. There are a few ways are there. One by one I am reciting you. Just you listen. You can go through the book also. First thing, it is energy remain constant through the system and surrounding. This is one way. This is also first law of thermodynamics. Energy remain constant from the system and surrounding. Second thing, that is if one form of energy disappears, there is the equivalent amount of another form of energy is produced or appears. Are you clear that? When one form of energy is disappear, the equivalent amount of another form of energy is produced or appeared. That is one way of explaining the first law of thermodynamics. And as you know very well, that is energy of conservation. What is that? The energy can neither be created nor destroyed. It may be changes from one form to another. Energy can neither be created nor be destroyed, but it may changes from one form to another. This is one another way. Then there also one more way is there, that is the internal energy change. The internal energy change, that is equal to the energy passed through the boundary as a heat and work. The internal energy change, that is equal to internal energy change del U, that is equal to, that is the energy passed through the boundary as a heat and work. Then final form of exponents of first law of thermodynamics, that is the heat and work are two forms that can changes the internal energies of the system. Okay, or heat and work only two way which changes the system's internal energy. Heat and work, the two factors which can changes the system's internal energy. These are the 5 different ways of first law of thermodynamics. Simply we can say that is there is no change in the energy in an isolated system, though it may changes from one form to another. That is a mathematical expression you want to give the first law of thermodynamics, that is a del U equal to Q plus W. Okay. Now then you can go with the way, what is the various way to express the first law of thermodynamics, which I am recited now. Five way you can recite the first law of thermodynamics. That is then we can go to the mathematical calculation of first law of thermodynamics. This is the first law of thermodynamics, that is del U equal to Q plus W. Okay. At case number 1 we can see for cyclic process. For the cyclic process, that is del U equal to change in energy 0. For cyclic process, that you have already studied in the introduction of thermodynamics. For cyclic process, del U change in internal energy, that is equal to 0. Then you substitute in the first law of thermodynamics, that 0 equal to Q plus W. Okay. Then Q equal to minus W. That means the quantity of heat is supplied, that is equal to work done by the system or done on the system. Okay. For cyclic process del U equal to 0, then if you substitute this value to the first law of thermodynamics, you may get the Q equal to minus W. It means that the quantity of heat supplied to the system is equal to the work done by the system. Okay. Then case number 2. For isochoric process. For isochoric process, del V equal to 0, that is you know very well. Del V equal to 0, volume constant. Okay, change in volume is constant. When you apply to that thermodynamics first law, del U equal to Q plus W. You know very well W equal to P minus del V, that is already known. The work done will be equal to minus W. Then del U equal to Q minus P del V. Applying this condition for isochoric process, del V equal to 0, then that is Q. For isochoric process, change in internal energy, that is equal to quantity of heat is supplied, Q. Del U equal to Q at a constant pressure and volume. Okay, constant volume. Because isochoric volume constant at a constant. That is for isochoric process, change in internal energy, that is equal to Q, quantity of heat. Okay, at a constant volume. Likewise, case number 3 for adiabatic process. Adiabatic process, that you know very well, that is Q equal to 0. Q equal to 0. For adiabatic process, Q equal to 0. You substitute in the del change in internal energy, Q plus W, that is first law of thermodynamics. Now Q equal to 0. Del U equal to, that's not like P. Del U equal to W. Now what it implies that is a change in internal energy, that is equal to that is equal to work done. Okay, when a Q equal to 0, that is equal to work done. Okay, here change in internal energy, that is equal to quantity of heat applied, that is equal to for a isochoric. For adiabatic process, del you change in internal energy, that is equal to work done. Then case number 4, isobaric process. Isobaric process, pressure is constant. Okay, at a constant pressure constant. At a constant pressure, if you write that equation, del U equal to Q plus W. Okay, then del U equal to Q plus W, you know very well, W that is equal to minus P del V, that is we have seen. Okay, minus P del V. Okay, it means that the quantity of heat applied, that is the energy, heat energy is, there is a amount of heat is spent for the PV work done. Okay, then total internal energy you want to change in internal energy, that is equal to the amount of heat is supplied minus P del V. That means there is some energy spent for the PV expansion, work expansion, PV work expansion, there is some energy spent. So total energy, the heat energy, that is not equal to del U. The internal energy change del U, that is equal to the total energy, heat energy supplied to the system, that minus some energy is less, where the energy is used for this, that is PV expansion, work expansion, the energy is used. So net, if we supplied 100 joules of heat energy there were few amount of energy supplied or used for the PV work done. Okay, for example 20 joules are supplied, then total internal energy change, that is not equal to 100, that is 100 minus 20, that is equal to 80. Okay, for isobaric process. These are the different process how the internal energy and first law of thermodynamics applied. Once again I am repeating this. For a cyclic process, in change in internal energy del U equal to 0, for isothermal expansion del U equal to 0, then the equation will become Q equal to minus W. Here the quantity of heat is supplied to that decrease in the work done. And the quantity of heat is supplied, that is all are equal. Then isochoric process del V equal to 0, del V equal to 0 means then del U equal to Q, that is change in internal energy, that is equivalent to the quantity of heat supplied. Okay, then here adiabatic process. Adiabatic process, as you know very well, there is no change of heat, exchange between the system and surrounding, that is equal to Q equal to 0. Then del U equal to W, it means the internal energy, that is equal to work done. Okay, or decreases in the energy, that is equivalent to that work done. Change in internal energy, that is equal to work done. For isobaric process at keeping the pressure constant, at a constant pressure, then the equation will become del U equal to Q minus P del V. That means that amount of energy supplied is, some of the supplied energy is used for the PV work expansion. So net change in internal energy, that is equal to del U equal to Q minus P del V. Okay. Next, let us move on to the enthalpy. So enthalpy. Enthalpy, it is denoted by H. Okay, enthalpy is a heat content. Heat. Okay, it is a heat content. It is a state function. Enthalpy can be given by H equal to enthalpy. It is a sum of the internal energy and the product of pressure and volume. It is enthalpy is nothing but a sum of the internal energy and a product of pressure and volume. This is called the enthalpy. Okay. Now the system changes to initial to final, then change in enthalpy. Del H, that is equal to change in enthalpy. from the initial to final or 1 to 2, system 1 or 2, state 1 to 2 or initial to final, that we can take del H equal to U plus PV, then del H equal to del U plus P del V. P del V. That is sum of the change in internal energy plus the product of pressure and the change in volume. That is a enthalpy change. H is the enthalpy, del H is the enthalpy change. So enthalpy change, enthalpy is a state function. It is a state function. State function. Enthalpy is a state function. Heat content. The amount of heat absorbed or released is called enthalpy change or H. Enthalpy. Enthalpy is nothing but in an entire system, the amount of heat released or absorbed during the process is called enthalpy or enthalpy change. Okay, state function. Enthalpy state function. It is depend upon the temperature, U and pressure. All state variables. Temperature, internal energy and pressure. It is a state function like. Okay. At a constant pressure, enthalpy change del H equal to enthalpy change del H equal to Q, quantity of heat at a constant pressure. At a constant pressure, enthalpy change del H equal to quantity of heat supplied. Okay, amount of heat supplied. So at a constant pressure it is like this. You know very well heat. When for these are two processes are there. One is a exothermic process. For exothermic process, from the system, what is the exothermic process? Heat is released from the process system. So heat is released mean, what about the Q value? Q value is less than that of the 0. Okay, because heat is released. Quantity of heat is released mean it is less than 0. So Q equal to negative. Q equal to negative. Q equal to negative for the exothermic process. When the Q equal to negative, what about the del H? If you apply there, del H also negative. So the process is exothermic. Exothermic, during the process heat is released. That is called exothermic. Those process, if a process is exothermic, heat is released, then it is less than 0. Quantity of heat, Q value is less than 0. Then Q equal to negative. Since Q equal to negative, del H also will be negative for a exothermic process. If it is endothermic process, it is a endothermic process. Endothermic process. What is called endothermic process? The process in which heat is absorbed, intake. The process in which heat is absorbed, heat is intake. Those processes called the endothermic process. If a heat is released, that is called exo, giving out. Heat is intake, it is absorbed, then it is called endothermic. For endothermic process, Q is greater than 0. Q is greater than 0. For endothermic process, Q equal to greater than 0, then Q equal to positive. Since Q equal to positive, del H also positive. Del H also positive. Okay. Since Q equal to positive, del H also positive. This question may be asked, what about the enthalpy change in a process? If a process is exothermic, then the del H value negative. Okay. The process is endothermic, del H value positive. At a constant pressure, for a closed system, del H equal to QP. Okay, Q, heat, amount of heat content. From this, for the exothermic process, what about the for exothermic, because heat is released, since heat is released, Q value less than 0, then Q value less than 0, that means Q equal to negative. Since Q equal to negative, del H also negative. For endothermic process, the energy absorbed from the process. During the process, energy is absorbed or energy is taken out, heat energy is taken out. So the Q value will be greater than 0. Then Q is positive. Since Q is positive, del H also positive. So we can say what is the process. If you say the process is exothermic, definitely del H value negative. If a process is endothermic, definitely del H value will be positive. Okay. Then let us see about the relationship between the U and H. The relation between the H and that is enthalpy and internal energy. How we can relate? So what is there for a system on state 1? For initial state, H, that is general formula is H equal to U plus PV. Okay. If a system 1, state 1, or a initial state, or initial state, the formula will be H1 equal to U1 P already constant V1. For final state, that is H2 change in enthalpy, U2 plus P. That is the enthalpy of initial state, this is enthalpy of final state. Okay. Now we are going to calculate the enthalpy change. Enthalpy change means final minus initial, that is equal to H2 minus H1, that is equal to U2 minus U1 plus P V2 minus V1. This is the way of it. Now what is the H2 minus H1? This is the change in enthalpy. Change in enthalpy can be given by del H. Change in enthalpy can be given by del H. Then U2 minus U1, final to initial, that is del U, plus pressure V2 minus U1, change in the volume. Change in the volume can be given by del V. Okay, del V. So this is the formula. Change in enthalpy can be given by del U plus P del V. Okay. As you know very well, now you apply the first law of thermodynamics here. First law of thermodynamics, it says that if you substitute here del U value, del H equal to, what is the del U value? First law of thermodynamics says that del U equal to Q plus W. That is first law of thermodynamics. You substitute here first law of thermodynamics, del H equal to Q plus W plus P W. Okay. We know that. What do we know that? We know that W equal to minus P del V. Okay. That is, we know that already. So substitute that here. Del H equal to Q minus P del V plus P del V. So minus P del V plus P del V cancelled. That is del H equal to QP at a constant pressure. So this way we have written the first the definition. Del H equal to at constant pressure. Del H equal to quantity of heat. Del H equal to QP. Okay, this is the relation. How we are relating. Del H equal to QP. Likewise, for a closed system, you are considering all our gases, reactant product. For a closed system, the gas is reactant product. How we can convert the relation between this? For example, if I am taking VI is the volume of a reactor. VI is the volume of a reactor. VF, volume of product. Volume of product. VF is a volume of product. Then Ni, number of moles of reactant. Number of moles of reactant. NF, number of moles of product. By applying the condition gaseous equation, because all the reactant and product are in gaseous state, already we have studied the gaseous equation PV equal to NiRT. Okay. This is for a reactant. If you write the equation for reactant like this, if you write the equation of product PVF, this is where VF is product, NF. Okay. PV equal to NRT, this is our equation. I for a reactant, F for the product. PVI equal to NIRT, PVF equal to NFRT. So what to do? The change in, if we compare this to pressure VF minus VI. Okay, that is equal to NF minus NIRT. This is where you can write it. Now, this is a P. We have changed final to initial, that is equal to P del V equal to N del N. Final minus initial, that is equal to del N, that is for gaseous G RT, del N G RT. So PV equal can be del N G RT. Del N, that is nothing but a change in number of moles for a gaseous reactant product. Okay, del N, there is nothing but a change in number of moles for gaseous reactant and a product. So del V change in volume for the reactant and product during the process. Pressure constant. Okay, like this we have. Now we are going to substitute to the equation. How do we have the equation there? Del H equal to del U plus, what is the P del V, that is already we have. Now you substitute P del V value to this equation. Del H equal to del U plus del Mg RT. This is the relationship between the del H and del U. Okay. For depending upon the number of moles you can have. If the different you have a same number of moles reactant and product, then the del H will be equal to 0. So you will have a del H equal to del U. The number of moles of reactant and product, it will be there. Then if you have a positive value of del Ng, then you will have del H is greater than that of the del U. If you have number of moles, del Ng value positive, here del Ng equal to 0, del H equal to del U. If you substitute this, del H equal to 0, then it is a positive value. Positive means something, del H is always greater than del U. Del H always greater than del U. If del Ng equal to negative, del Ng equal to negative, what will happen? Del Ng value negative, del H is less than del U. From the relation we can get. This is the relationship between the del H and del H and U. So once again we can recall this. This is most problems asked, one-word problems in both NEET as well as theory. They will be asking. You have to be very keen enough. It will be very easiest derivation like. Okay. See, normally enthalpy H equal to U plus PV. Okay. For initial state, initial and final state system to initial and final. I am considering for initial state H1 equal to U1 plus PV1. For final state H2 equal to U2 PV2. Then H1, the change in enthalpy H2 minus H1, that is equal to change in internal energy U2 minus U1 plus P V2 minus V1. So this is totally del H, this is totally del U plus P del V. Okay. So this is the relation formula. Then if you substitute the first law of thermodynamics here, first law of thermodynamics says that del U equal to Q plus W. Then del H equal to Q plus W plus P del V. As you know very well that we know that is W work equal to minus P del V. So if you substitute minus P del V in the relation, del H equal to Q minus P del V plus P del V. The minus P del V and plus P del V cancel. So that is at a constant pressure, change in enthalpy, that is equal to quantity of heat is supplied to the system. That is del H equal to Q. Then, for a closed system, all the reactant product in a gaseous state. If all the reactant product are in a gaseous state, let us have this equation like this. Volume of initial Vi, that is equal to Vi here, volume of the reactant. Because initially we are taking the reaction, Vi equal to volume of reactant. Vf is volume of the product. Ni, that is a number of moles of reactant. Nf, after the reaction, the product will be formed, number of moles of product. So, applying the gaseous equation, PV equal to nRT. For the reactant, if I apply the PV equal to nRT, PVI equal to NIRT. Okay. Likewise, if I apply the product, the gaseous equation, PVF equal to NFRT. Okay. Now, if we compare with these two, the change in P volume of final to initial, that is del V, P del V, volume number of moles of final and initial, that is a product minus reactant, that is del Ng RT. The G mean for all the reactant and product should be in a gaseous state. That's a G value. Del Ng equal to RT. Okay. Now, again you write the relation between the del H and del U. Del H equal to del U plus P del V. If why for we are calculating this, in order to substitute the P del V, del Ng RT we are substituting. After substituting del Ng RT, you can have three cases. Based on the del Ng value, we can relate the del H and del U. That means the enthalpy change and the internal energy change can be related by using the number of moles for the reactant and product, change in number of moles. So, if a change in number of moles, that is del Ng equal to 0, for some cases in a gaseous reactant product, if we take a number of moles are equal to the number of product. It is not always, sometimes. On those cases, del Ng equal to 0, you apply the del Ng value 0 here in this equation, the whole term will be 0, then del H equal to del U. That means, when the number of moles of reactant that is equal to number of moles of product, in that case, change in enthalpy equal to change in internal energy. There is a thing this that. Okay. Likewise, sometimes number of moles of product will be more than the number of moles of reactant. On those cases, you apply del Ng value positive. If a del Ng value positive, if you substitute this in the equation, del Ng value positive, del H is greater than that of the del U, because del U plus some value is added. Some value is added means del H value is greater. Then del H is greater than del U. That means, on those cases, when a number of moles of product is more, change in enthalpy will be greater than that of the change in internal energy. Then case number 3, if you take in some cases, number of moles of reactant is more than that of the number of moles of product. So if you apply then del Ng value negative, in those cases, del H is equal, less than that of the del U, because del U minus del Ng minus, here some value is reduced from the del U, so del H will be very less than that of the del U. Okay, these are the relation between the del H and the del U. Now let us move on to the heat of formation. Heat of formation that we can see here itself. Simply, the standard heat of formation. Standard heat of formation. Standard heat of formation. Standard heat of formation. Standard heat of formation is nothing but a change in enthalpy. Change in enthalpy when 1 mole of compound is formed from its elements at standard state. When it is a change in enthalpy, when 1 mole of compound is formed, 1 mole of compound is formed from its element at standard conditions, standard states. What are the standard conditions? 1 bar pressure and 25 degrees Celsius or 298 Kelvin, temperature 290. This is standard heat of formation. That is standard heat of formation is the change in enthalpy when a 1 mole of compound is formed from its elements at standard states. Okay. What is standard state? 1 bar pressure and 25 degrees Celsius or 298 Kelvin. For example, if we have some equations here, F is solid plus S solid to give a FES. Okay. Here del H F naught standard heat of formation, that is equal to 100 plus 4.2 kilojoule per mole. Kilojoule per mole. Likewise 2C, that is solid plus H2 gas energy and H, that is we are going to see now. It give a C2H2. Okay. For del H value, that is a minus, that's exothermic, that is plus 222.33 kilojoule per mole. Okay, this is way how heat of standard heat of formation we can give. It is a minus meaning it is exothermic, plus mean endothermic. Once again I am saying that what is the standard heat of formation? It is a change in enthalpy when a 1 mole of compound is formed from its elements at standard state. That is called standard heat of formation. It may be exothermic or endothermic. It is nothing but a change in enthalpy. It is denoted by del H. Okay, there is a change in enthalpy del H. For formation F we are putting standard condition 0. Okay. Thank you.